Okay, let's begin with another video. This video is going to be pretty specific to a very specific class of titrometric methods, so it will be categorized or classified under volumetric analysis. You oftentimes see this in a chapter where you're talking about titrations. And the reason why is because we're going to be considering very specific subcategories of titrations. And that specific subcategory was defined right here. Argentometric methods, okay? And basically all that means is it's going to be a volumetric method based upon titrating with a silver ion, okay? So the silver ion is going to be our titrant for these argentometric methods, okay? It's rooted in the old Latin name for silver. So we're going to talk about two very specific argentometric methods in this video. Oftentimes these are also covered in your textbook, and they have very specific names and they work very specific ways. So we're going to talk about how they work and what information you can get using them, just providing an overview, a quick overview. You can always find more details about these methods in your textbook or else in the literature, okay? So I'm just going to kind of provide a broad overview of this because they're not necessarily considered a super modern method of analysis. First one's going to be called the Volhard titration. It's a very specific titration. We'll see that in a second. It's also a back titration. It's going to involve the formation of a soluble colored complex at the endpoint, and that is going to signal when the titration is done, or it's going to signal our endpoint, okay? Second titration we're going to consider uses a completely different type of indicator. It's going to use an absorption-based indicator, and it turns out that the color of that indicator is going to change based upon the surface charge of a precipitate that forms in our reaction system. The surface charge is going to flip at the endpoint, at least that's the belief, and that is going to lead to a color change of a dye, and that's going to signal the endpoint. So let's talk about each of these in much more detail now, so we understand how they work. You may see a problem based on this during an in-semester exam and also on the final exam. So you need to at least have a familiarity with these methods, that they are argentometric methods, and how they work, okay? Now the Volhard method probably arguably is the more complicated of the two, and that's because it's a back titration. But before we talk about the details of the Volhard method, let's talk about what these methods will be used for. Generally speaking, if you're using an argentometric method, that is titration with a silver +1 ion, you are going to be determining anions, negatively charged ions, that are going to form insoluble silver salts. Okay, so they're going to react with the silver that you add from your titrant to form an insoluble solid, and thereby the coupling of the silver with the anion forms the precipitate. And from information involved in the titration, you can figure out how much of the anion was present. So that's what these argentometric methods are going to be based in, or rooted in the chemistry, okay? It's precipitation-based chemistry with an insoluble anion. Now the Volhard method in specific is a back titration. Back titration. This is an important bit of terminology. And generally speaking, in a back titration, what the analyst does is in the first step, they purposely add too much of a reagent that reacts with the analyte. So you over-add the reagent purposely, okay? You add an excess quantity. The reason for doing that is because that reagent that you add consumes 100% of the analyte. And there's a little bit left over once the analyte's used up. And then you can titrate the substance that you added back to equivalence, okay? And from doing a little bit of mathematics, you can figure out how much of the analyte was present. So let's see how the Volhard method works more specifically, okay? So again, it's going to involve the silver ion. So what's our experimental setup for this? Well, we're going to start with a beaker, and that beaker is going to contain our sample. We pipe out a known quantity of our sample that contains an anion that we want to measure. So maybe like chloride or fluoride or bromide, something like that, or just any anion that can form an insoluble silver 1 salt. So there's actually a pretty long list of those, okay? So we're going to start with the sample in our beaker. And then in the first step, we're going to add an excess quantity of silver plus 1 into our flask. So the sample was there, we purposely add in an excess quantity of silver plus 1, extra silver plus 1. When we do that, that silver plus 1 ion essentially forms a precipitate with the anion that we want to measure. Okay? So let's just say that in our example here, chloride is our analyte. That's what we want to measure. That's present in our sample. We add too much silver in step 1 to drive this reaction to completion. And as soon as we add the silver, in this flask we are going to get a precipitate of silver chloride. That makes sense? Now, what limits how much silver chloride we can make? Well, since silver was in excess, the amount of the analyte limits how much silver chloride we make. Okay? See where we're going with this? Hopefully so. Okay? Now, the thing is not only did I add an excess of silver in this step, I added a known quantity, a known excess. In other words, I know how many moles of silver plus 1 ion I pipetted into that beaker during this step. Okay? I know that because I know the molarity of the silver solution going into this. I've prepared it, I've standardized it, I know its molarity, and I also know the volume of the silver solution that I added. Okay? So my point here is I know the total number of moles of silver that was added in step 1. A portion of that silver is going to react to form this precipitate, but not all of it because I've added an excess. Okay? This number in the equation that I wrote here is going to be the amount of the precipitate that I formed, or it's going to be correlated with the amount of precipitate that I formed. Okay? Or directly related to the amount of precipitate that I formed. But the thing is I'm still going to have a little bit extra silver floating around in my beaker down here. Silver plus 1 ion. This is unprecipitated. This is this form. If I could figure out how much extra silver plus 1 ion is floating around in this beaker after the precipitate forms, I could figure out how much chloride I must have had present. And the reason why is because I know how much silver ion I added, because I know what volume of silver solution I pipetted in. I know the molarity of the silver, so I know how many moles I added in step 1. If I could figure out how much excess I had, I could figure out by difference how much chloride I must have had. And that's the basis for the Volhard method. In a second step, after you precipitate this substance, you may have to filter it off to remove it from your reaction system. Okay, that's because it can possibly redissolve and interfere and cause all sorts of problems. Okay. The next thing that we do in step 2 is we add a source of iron 3 into our sample mixture. It may seem confusing why we add the iron 3, but the reason is going to be clear in step 3. It's actually going to help serve as an indicator. Okay, and we'll see how that works. So after we filter the precipitate and add our iron, the next step is to do a titration. We do our titration with potassium thiocyanide, a standard solution of potassium thiocyanide. What we do is we fill up our burette with our KSCN solution of known concentration, and we dispense a volume needed to complete the titration. Well, what titration are we actually running here? It may not be clear. Well, the key equations to understand for the actual titration in the Volhard method are shown here. What we're going to do is react the thiocyanide ion with silver plus 1 to form an insoluble silver thiocyanide. So the silver reacts with this ion to form this precipitate. Now let's think about that for a second. What are we trying to achieve by running this titration from this burette? Well, remember in step 1 we said we added a known excess of silver? Some of it reacted to form this, some of the silver plus 1 we added reacted to form this chloride salt, but we still had excess. We had too much of this. So if we do a titration to figure out how much extra we had, that's going to be useful information for us. So what do? We titrate with this ion to form this solid. And when this stops forming, well, we've reached our equivalence point or our end point, and we know we could backtrack out how much silver must have been present in excess if we know the molarity of this stuff and we know the volume of this that we titrated. So that's going to be kind of our measurement strategy here. The only problem is that we don't have a good indicator yet. Now remember in step 2 we added the iron 3? There's a really good reason for that. The reason is shown in this equation. The only purpose of this last reaction is it serves as our indicator. It turns out the iron 3 plus will also react with the thiocyanate ion to form this complex ion in solution. It just so happens that that complex ion, when it's dissolved in aqueous solution, is kind of like a bright red color. So that actually serves as our indicator, that color change to a bright red color. And the beauty of this reaction with the iron is that the iron binds this ion less effectively or less aggressively compared to the silver. So it turns out that these reactions are sequential. Reaction 1 happens to completion, and only if I run out of my iron does reaction 2 occur. So as soon as I run out of my silver, reaction 2 begins, and I form this blood red colored complex in my solution. So it's a really nice indicator for this first reaction's completion. Alright, so what do we get out of this information? Well, from the volume of my standard potassium thiocyanate solution and the molarity of that solution, both of which I measure or know, I can compute the moles of SCN added. That number of moles to reach the end point must correlate in a 1-to-1 fashion via the stoichiometry of this reaction with the amount of silver plus 1 that was floating around in the beaker. Now, why is that important? Well, back to the beginning, didn't we say we added an excess of this? Some of it precipitated this salt, but some of this was left over. In step 3, I figure out the number of moles of this that remain in my beaker, that were left over, that were excess, okay? So my mathematical equation here that kind of drives the quantitation of this method, this term here on the far right, the number of moles of silver that reacted with the SCN minus 1, that's how much was in excess from step 1. We determined that in the titration. Okay. We knew how many moles of silver we added because remember it was a known excess quantity. We pipetted in a known excess quantity of a specific concentration. So I know how many moles of silver I added. So I know this number, and I know this number, and by conservation of material or conservation of matter, I know that the total amount of silver that I added to my beaker has to equal the amount that reacted with the SCN minus in this step, plus the amount that reacted with my sample, or my analyte. Okay? So basically we're just tracking where the silver goes. Some of it goes to form this solid, some of it goes to form this solid, and if I add the amount of silver here, plus the amount of silver here, that has to be the amount that I added. Okay? So the titration gives us one of those numbers. I know how much I added, and by difference or subtraction I can figure out how much must have reacted with my sample ion. And in doing that and linking back to the 1-to-1 stoichiometry, I could use this information to figure out how much chloride must have been present in my sample. Okay? So this is the basis of the Volhard method. It's a back titration. It's a little bit confusing. You kind of have to remember the order of things here to remember how this works, and then also remember the iron is added, which essentially serves as an indicator. Okay, but the neat thing about that reaction is that it doesn't happen until the silver is completely used up, and then we get that nice red color that forms in our solution. So that's the Volhard method, one of these argentometric methods. There is another argentometric method that may be of interest to you. It's the Phasians method. This also is used to determine anions which form insoluble salts with silver plus 1. Same general purpose as the other method, the Volhard method that we just discussed. The main difference is this is more of a direct titration, and we use a different indicator here than we did before. So if I was going to set up an experimental apparatus for this, what I would do is I would set up a burette with a standard solution of silver plus 1. That's an aqueous solution of silver plus 1, known concentration. I'd have my sample down here. Again, I'm going to use the idea that I'm going to analyze for chloride via this method. Okay, it's just kind of a simple example because, of course, chloride binds in a 1-to-1 ratio with silver plus 1 to make silver chloride solid. Okay, so that's going to be our reaction that we're going to run once we start adding the silver. Now, our sample has the chloride, or the analyte of interest. It's going to be an anion again. And what I'm going to do is I'm going to add an indicator compound directly to this mixture now. The indicator compound that's used in this titration is dichlorofluorocene. Its structure is right here. So the 2 chlorines, hence the name. Okay. This indicator is going to change from a greenish yellow fluorescent color, kind of like a highlighter type of color, like a yellow highlighter, to a pink color at the end point, and that's going to signal our end point. The way that this is believed to work is another interesting part of this titration. Okay, and what I've done here is I have a figure in the middle. It's basically meant to show before and after the equivalence point, respectively, in terms of what's happening with this dichlorofluorocene dye. So it's kind of a little bit of a story, so let's just kind of go through it and jump in. Once I start adding my silver drop-wise here into this beaker, silver chloride is going to start forming essentially immediately upon the first drop, because this stuff is not very soluble at all. Alright, so I'm going to start forming silver chloride solid. Now, on an ionic type level, you can envision the silver chloride looking something like this picture here, where we've got silver ions and chloride ions, and they start forming some sort of crystal lattice. Okay, this is just kind of a cartoon picture. It's not necessarily representative of three-dimensional reality in terms of the cubic structure of this, but you get the idea. The positive ions, negative ions, they kind of pack together. Okay, kind of almost like oranges at a grocery store or something of the sort. Now, before the equivalence point, before I add enough silver, what's going to happen is the next layer of my negative chloride ions are going to start to kind of accumulate here at the surface of this crystal as it's forming. And that's going to lead to a slightly negative surface charge. Okay? Now, if one of these indicator molecules comes into the surface, okay, and I'm just going to abbreviate that here as ion 2- to be consistent with the other drawing. It can adsorb to that surface and interact with the surface, which has a negative surface charge. It just so happens that in such a case, this indicator molecule is believed to yield this kind of nice greenish yellow color. Okay? Now, after the equivalence point, a different situation exists. And the reason why that is because think about the situation after the equivalence point. After the equivalence point, I will have added enough silver to titrate all of my chloride ion. And in fact, if I'm after the equivalence point, I'll add a little bit of excess. Again, that's titration error, but I over-titrate ever so slightly. Okay? If that's the case, now I've got too much silver plus 1 ion. And those silver plus 1 ions are going to start to accumulate at the surface, like they were trying to form the next level, if you will, of this crystal. Okay, but there's just insufficient chloride to sort of titrate it off. Okay, but we're going to have this positive surface charge as a result of this. The implication of this is when the indicator molecule comes in and adsorbs to that surface, it will exhibit a pink color. So it's believed that this indicator dye changes from greenish yellow to pink as an indicator of the surface charge density on this insoluble salt that forms within our beaker. Okay? And because that charge density flips sign right at that equivalence point, the dichlorofluorocene is a useful indicator of when we reached the end point of our titration. So this is the basis for the Phasians method, another Argentometric method. So with that said, this video on Argentometric methods has concluded. Thank you.